No, you're not about to see a sequel to Metropolis, but something you can create directly from your computer. Have you ever wondered how to bring a cinema icon back to life? After the intro, I'll explain everything in detail. The short clips playing in the background were all generated locally on my computer. But how was that possible? The heart of this revolution is Hunyuan Video, a generative artificial intelligence model developed by Tencent and released, in some versions, as open source. This tool allows you to create videos from a simple text prompt in English. Compared to other similar models, Hunyuan Video represents a significant leap in quality, offering results comparable to commercial solutions like Runway and Sora, with three major advantages: the ability to generate videos locally at virtually zero cost, no content restrictions, and almost unlimited customization freedom. Much of this customization is made possible thanks to LoRAs, low-rank adaptation, which are mini-models that can be trained locally and attached to the main model during generation. LoRAs can be trained on specific elements, such as characters, visual styles, or particular scenarios. In the case of the initial video, for example, the LoRA was trained using frames extracted from Fritz Lang's film Metropolis, allowing the recreation of the distinctive aesthetic of the famous robot protagonist. Following this guide, I'll show you how to train your LoRA locally on your PC. Similarly, you can generate a LoRA to replicate a cinematic style, generate the face of a famous character, recreate an architectural building, and much more. I know this topic may seem a bit technical, but don't worry. With a little effort and passion, you'll discover an incredible world. Are you ready? Welcome to the rabbit hole. Let's take a look at the hardware and software tools we need to cook this delicious recipe. To get started, we need a PC. Although Linux is often preferred for AI applications, in this video, I'll refer to Windows. A recent CPU, at least 16 GB of RAM, a fast and spacious SSD. But the real core of everything is the graphics card. To train a LoRA effectively, an NVIDIA RTX with a good amount of VRAM is essential. 8 GB may not be enough for more complex models. I use an RTX 4060 Ti with 16 GB. To make the process more accessible, I'll follow a step-by-step guide on training a LoRA using a graphical interface. This helps avoid manually running Python scripts, which can seem daunting for beginners. So let's make sure we have everything we need as indicated in the guide. Some of these programs might already be installed, but it's always best to check. You can find all the links in both the guide and the video description. CUDA. Download it from NVIDIA's official website. I recommend one of the 12.4 versions because, after various tests, I encountered issues with other versions, even more recent ones. MSVC, Microsoft Visual C++. It's part of Microsoft Visual Studio. Follow the guide's instructions to install it. At the end, verify that it's correctly installed by typing CL in the command prompt. The package containing the code and GUI from TT-Planet Cohere. You can download it from the link provided in the guide. The file is compressed and password protected. The password is also in the guide. To extract it, I recommend using 7-zip. If you don't already have it, it's an excellent open source tool for managing compressed files. The package already includes an embedded version of Python, so there's no need to install it separately. To have a partially translated GUI in English, replace the file with the one provided in the guide. In addition to the GUI, other files will be needed for the LoRA training process. You can place these files wherever you prefer. I chose the directory structure shown in the video. The diffusion transformer, DIT, the actual model for image generation. The variational autoencoder (VAE) file, a type of neural network used for data generation and compression. 2 text encoders. Text encoders are AI models that transform text into numerical representations. 2 are used to improve generation quality. A .toml file will also be needed. This is a simple text file used to configure the dataset training. You can find my example in the video description. The main values you might need to modify are: resolution, defines the size of the images used in training. Cache_directory, indicates the folder where temporary caches will be saved. Image_directory, is the folder where images and corresponding .txt files are stored. Make sure to correctly set these paths according to your configuration, paying attention to use double backslashes instead of single ones. Otherwise, the path won't be recognized. Now that everything is ready, we can proceed. The first step is to prepare an adequate dataset, meaning a collection of images, all of the same dimensions, of the subject we want to teach the model. In my case, I extracted 12 frames from the film Metropolis, selecting scenes where the robot protagonist appears from different angles and in different poses. This is a small number of images, but in this case, they prove to be very effective. In other cases, datasets of hundreds of images may be required, significantly increasing processing time. For each image, I added a description with the same name as the image but with a .text extension, including details such as facial expression, camera angle, clothing and posture, background and objects present. To uniquely identify the robot, I used the string M4R14, a sort of magic word that cannot be confused with common English terms. This way, when I generate images or videos with the model, I can use this word to ensure that the LoRA is applied correctly. I then saved the images and descriptions. How did I create the descriptions? You can write them by hand, but to speed up the process, I used artificial intelligence, leveraging ChatGPT, web version, OpenAI APIs, a local language engine. This way, I obtained 3 distinct sets of descriptions for my 12 images, which I can use individually or combine for more effective training. You can find the links to these datasets in the description, so you can try them out too. In a future video, time permitting, I will show you in detail how I generated these descriptions and which tools I used. And now, let's get into action. To start, I opened the folder where I had unpacked the GUI and double-clicked on the .bat file. A command prompt opened, and after a few seconds, it displayed a link, usually an HTTP address on localhost at port 7860. At that point, I copied the link into my browser and found myself on the main screen, which is divided into several panels. In the panel labeled Pre-caching and later Hunyuan Pre-caching, I uploaded the .toml file I had prepared earlier, set the paths for the VAE files and the 2 text encoders, and clicked the Start button. This step is necessary to generate the image cache files, which will then be used in the actual training process. At the bottom of the screen, I saw various messages indicating the progress of the process. The waiting time can vary. In my case, with a small number of images, it only took a few minutes, but it could take longer depending on the number of images. Once the pre-caching was complete, I moved on to the training panel. Here, I uploaded the same .toml file again and then set the number of epochs, which are the training cycles. Let me tell you right away, the more epochs you set, the slower the training will be. From my experience, going beyond 20 epochs doesn't significantly improve the quality of the results, but I suppose this also depends on the images used. My advice is to experiment and see what works best for you. After choosing the number of epochs, I specified the folder where I wanted to save the generated files, set the path for the DIT model and the other 3 files as I had done in the pre-caching step, and uploaded the prompt_file.txt found in the GUI installation folder. Warning: the system creates 1 LoRA per epoch, so with 10 epochs, I ended up with 10 files, each over 300 megabytes, totaling around 3 gigabytes. Make sure you have enough disk space. At that point, I clicked the Start button and let the computer do its work. The processing time varies greatly. It can take from less than an hour to several days, depending on the GPU, the number of images, their size, and the number of epochs. To give you an idea, with my RTX 4060 Ti, it took about 8 minutes to train a LoRA with 12 images at 512 by 512 pixels for 10 epochs. But when I tried with 36 images and 30 epochs, The process took an entire night. This last LoRA is the one I then used to generate the opening scenes. At this point, the only thing left was the conversion to make the LoRA usable in my projects. I went to the LoRA conversion section, loaded the most recent .saffa-tensors file from the output folder, usually named LoRA.saffa-tensors, selected where to save it, and clicked Convert LoRA. After a few seconds, my LoRA was ready to use. And now? To use it, I loaded the file into ComfyUI, an application that, among many other things, allows you to generate videos by combining Hunyuan video with a newly trained LoRA. Its strength lies in the use of nodes and workflows that hide the complexity of Python scripts. If there is interest in the topic, I will show you in detail how it works in one of the next videos, but you won't have trouble finding useful tutorials online. Warning: always remember that training and using LoRAs must comply with current regulations, especially those related to privacy and copyright, avoiding the creation and distribution of misleading or deceptive content regarding their artificial nature. Thanks for following along. In the next episodes, I will cover aspects I have skipped, such as using ComfyUI for video generation or how to use LM Studio together with a language model and my C# program to automatically generate image descriptions. I will also explain how to write Python scripts to automatically extract keyframes from a video and adapt them for use as a dataset. If you have any questions, corrections, or suggestions, leave them in the comments. If you liked the video, give it a thumbs up and subscribe to my channel. This will encourage me to create more videos, including English versions for those of greater interest. Happy experimenting, and see you next time.